Welcome friends. So we are discussing Fourier series. Initially we have discussed the Fourier series expansion, the definition of Fourier series expansion. From there we have derived the formula of A0, An and Bn. From there we have also studied different kinds of symmetry, and we have understood that for a given type of symmetry we have different calculation strategies. So to illustrate those facts, we shall briefly demonstrate few problems. Now let us have this waveform. It is the quarter of the waveform is given, that is 0 to t, from 0 time to t0 by 4. It is the quarter of waveform is given. Now you must complete the waveform. To understand the concept regarding the Fourier series coefficient A0, An and Bn, this problem is extremely helpful. So we have different conditions. For each of the condition you need to complete the waveform. So let us first try to understand one by one. So first we have A0 and An existing. So if we have A0 and An existing, that means Bn is 0. That means it must be a even symmetric function. Then it must be a even symmetric function. So what is even symmetric function? Even symmetric function, you know, it is a symmetrical about the y-axis. So it is a even symmetric function, so it should be minus t0 by 4. So this becomes the half cycle. This becomes the half cycle. Becomes t0 by 2. Now with the continuation with this A0 and N, if existing, then A0 means it must have, it is a DC value, so it must not have some negative value, right? So with the continuation of this, the complete waveform should be like this. This is the complete waveform. So it should be 3. It should be t0 by 2 should be minus t0 by 2. So this is the complete waveform. Now if you have this waveform, you must have A0 and N, but you should not have any Bn. Now let us try to understand next thing. Bn exists for odd n. Bn exists, so An, A0 and An should be 0. They are 0. So we try to understand, since A0 is 0, there must be negative value. There must be negative value, other than that it is not possible. So Bn, so let us complete the half cycle first. So it should be the half cycle, so minus t0 by 4. So you see Bn existing for odd n, that means it is a odd function. Odd function, so odd function, you know, it is a symmetrical about origin. Okay, so for this type of function A0 and N cannot be existed, so that is clear, because it is an odd function. Now additionally it is a Bn is existing. Now for odd function Bn is existing, that is true, but additionally it is given Bn is existing only for odd n. That means they are existing only for these values B1, B3, B5. So you must make the full waveform keeping in the mind that it must be half wave odd symmetric. Now half wave of odd symmetric means if you consider any time, that means this time, and if you consider t plus t0 by 2, then odd means it will produce negative value. So at this time it is giving the negative value, so at this time it must be giving positive value. So the complete waveform will be this. So complete waveform should be like this, or should be in this way. Both will be correct, T0 by 2 and this will be 3 T0 by 2. So this is a half wave odd symmetric. Again, so if you consider another time T1, so this is producing this value, let us say C1. So if you consider T1 plus T0 by 2, it will be giving negative value, that is minus C1. So this will be the correct representation for this case, Bn existing only for odd n. And now the reverse thing is given, Bn existing but for even n. So the first part of the same, minus T0 by 4. So for this kind of waveform it is odd. So for odd function A0 and An does not exist, cannot be existed, okay. But it is even. So even means what? Even means it is actually f of t plus t naught by 2, that should be is equal to f of t. So if you consider any negative time, let us say this time, so it is producing this value actually, let us say C1. So if you add T1 plus T naught by 2, so it must produce the same value as C1. So that is why the correct form should be like this. This is T naught by 4, so this should be T naught and this is 3 T naught by 4. Lastly, it is mentioned A0 existing but for odd n. Now it is a strange situation, A0 is 0, Bn is also 0. So An is only existing, An is only existing but for odd n only. Okay, so let us try. So since An is there, then let us complete first the half cycle. So it should be the half cycle, minus T naught by 4. It is the half cycle, right? Now since A0 is 0, then it must possess negative part, otherwise A0 cannot be 0, right? So it should be a negative part. Now in addition to that, you have to check An existing for odd n. So when n odd will be the case of a half wave odd symmetric, right? Half wave odd symmetric. So what is half wave odd symmetric? F t plus t naught by 2, that will be is equal to minus ft. So if you consider any time, so let us consider this time, and if you extend t plus t naught by 2, so it will produce the opposite value. So the correct form is this, T0 by 2, 3, T0 by. So please try to understand the same, these are all same waveforms actually. It is arranged in a different manner actually. Depending on them, different A0, An, Bn for different condition will be existing, right? The first one, the complete waveform is like this, it will be go like this, right? The second waveform is like this. Again it's like this, right? It's go like this. The third waveform is simple at this type of nature. In this way, and fourth waveform is this. So every time it is a symmetrical wave but differently arranged, and depending on that nature, different coefficients will be existing. So this is a very nice example through which you can understand, you can learn the methodology or process by which different, in how many ways or how many different ways, for what other conditions A0, AN and BN will be existing. So let us move to our next problem, which is figure 7. It is a square wave given. This is a square wave given. So you need to evaluate Fourier series expansion. It's a very important problem. So as you can see, it is a positive, negative, both things are there. So A0 is not 0. A0 must be 0, sorry. AN also be 0, because if you extend this waveform in the negative direction, it will be look like this. So it is symmetric about odd. It is symmetric about origin. So only Bn will be there. So let us try to evaluate. Now, in addition to that, it will also possess the property of half wave of odd symmetric. That means it is T plus T0 by 2. That will be is equal to minus Ft. So you can directly substitute En, that should be is equal to 4 by T0 integration Ft sine n omega naught t dt. Now integration should be carried out from 0 to T0 by 2. Now you must put n is equal to 1, 3, 5, 7 and so on. So from 0 to T0 by 2, that means within this zone the Ft value is 10. Ft value is 10. So you can take this one as out, 4 into 10 by T0. Integration of sine, it will become cos n omega naught t dt, omega naught t, of course with a negative sign. Now you must put the limit T0 by 2 to 0. And with that we must have this term, that is n omega naught t, n omega naught t, right? So you see that 40 by n, now omega naught t naught is equal to 2 pi, that is in here, that into minus 1, now cos in omega naught, now in place of t you substitute t naught by 2, and then it will be minus cos 0, that means it is 1. So if you substitute, you will get the result Bn is actually this. So Bn should be evaluated as 20 by n pi from this result. Now omega naught t naught is equal to 2 pi, so it will be 2 pi by 2, that is cos n pi, cos n pi minus 1, and with a negative sign of course. So when n is equal to 1, when n is equal to 1, so b1 should be 20 by pi into minus 1 into minus 2, that will be equal to 12.74 if you solve. And when you substitute n is equal to 3 from this expression, you will get b3 is equal to 4.25. Similarly, if you substitute n is equal to 5, you will get this. So if you substitute these values respectively, you will get ft, that will be equal to b1 sine omega naught t plus b3 sine 3 omega naught t, b5 sine 5 omega naught t, and so on. So you have evaluated b1 as 12.74 volt, so it will be 12.74 sine omega naught t, b3 will be 4.5 sine 3 omega naught t, and then we have evaluated the final term 1.27 sine 5 omega naught t, and the higher order harmonic terms are insignificant. So this is the Fourier series expansion of this waveform of this square wave. Now let us proceed to the next problem. Now it is again another important problem. And now we have this Fourier series. This chapter is mainly focused on the periodic waveform. Now we have already mentioned that periodic waveforms of 4 symmetrics: odd, then even, then half wave, then half wave odd, then half wave even. We have mentioned, and we have also understood for odd Bn will be existing, for even only A0 and An will be existing, for half wave odd An and Bn will be existing for n odd, and for half wave even A0 will be existing, An and Bn will be existing for n even. So we have already seen these aspects. Now there are few periodic waveforms, they do not possess any symmetry. Neither they are odd symmetry, nor they are even symmetry, nor they are half wave symmetry, nothing. But still they are periodic waveforms. So this is a perfect example of a waveform as illustrated in figure 8. This waveform actually tells that it is actually periodic, because for every naught after a t0 time, this time period, it repeats itself. However, it does not possess any symmetry, neither half wave nor odd nor even, nothing. So with the help of this example, or with the help of these derivations or all this information, we can have the idea that which is to be calculated, A0, An, Bn, then which is to be calculated of what period or what waveform. Okay, but if a waveform does not have any symmetric at all, or does not have any symmetric nature, and then how should we decide in which way we should follow? And the answer is, from this waveform you must you must generate the half wave, you must generate odd and even function of it. Why? Because you see, suppose if I write ft in this fashion, ft that is equal to half ft plus f of minus t. This is one. And second part I am writing half ft minus f of minus t. Just I am writing in this fashion. You see, this first part is called even function. Even function of this, parent or mother function, and the second function is called odd function. So any periodic function or periodic waveform which does not possesses any even symmetry or odd symmetry can be made by this to evaluate or to form even part of it and odd part of it. What is even function? It is ft plus f of minus t by 2. What is odd part of it? ft minus f of minus t by 2. So if you have ft, then you must calculate or you must construct f of minus t. Just you need to reverse your time. So it is illustrated that in the first figure, it is actually the diagram of ft. It is actually the diagram of ft. And in the second diagram, it is actually the diagram of f of minus t. Okay, just we revert or we opposite the time limit. Now as per the even part is concerned, f of even t, so we add them. And then divide it by 2. So if we add them, then you see this 10 volt and 0 volt, it will become 10. And from this interval 10 and 0, this will become 0. So we will get a line like this. We should get a straight line like this. Now why should it is 5 volt? Because it is by 2. So f of t plus f of minus t, this will 10 volt. Throughout 10 volt by 2, it will be 5 volt. So it will be f of even function. Now what will be f of odd? So it will be, now subtract f of t minus f of minus t. Now in order to do the subtraction, this should be multiplied with minus 1. This should be multiplied with the minus 1. So effectively this will become this actually. So when then you subtract, then it will give a square wave like structure like this. So this is the odd part. Okay. So the even part is 5. That is already mentioned. Now the Fourier series expansion of this waveform is already done in the previous example, where we have 100 volt where we have 10 volt. Now in this case we have 5 volt. So the answer should be something like this. So the Fourier series expansion of this waveform is this. This is the 5 is the even part, and entire this thing will be the odd part. Now let us move to our next problem. That is this waveform, this triangular waveform. We need to Fourier series expansion. We need to evaluate Fourier series expansion. Now let us split this function into 3 parts. First one is from 0 to t naught by 4. So this is actually this equation. So these 3 split up. One is from 0 to t naught by 4. Then from t naught by 4 to 3 t naught by 4. Then finally 3 t naught by 4 to t naught. This actually this split is already discussed in the previous session. That is we evaluated the Laplace transform of this waveform previously. Now let us try to analyze. Let us try to analyze this waveform. First of all, as you can see from the diagram, it is actually symmetrical with respect to origin. So it is a odd function. So A0 will be 0, An also be 0. So only Bn will be there. In addition to this, if we consider any time, if you consider any time t, and with that time if you proceed half cycle forward t0 by 2, so with the same value, so it will giving the negative value. So it is satisfying f t plus t naught by 2, that will be is equal to minus ft. So Bn is existing, no issue, but only n odd, with n odd. So with this problem, we only evaluate Bn with n odd. The formula will be 4 by t naught, 0 to t naught by 2, ft sin n omega naught t dt, with n is equal to 1, 3, 5, 7 and so on. So if we split into 3 parts, 1, then 2, and okay, so that integration should be carried out into 2 parts, because this is not actually, this part is not utilized anymore, it's not required actually. So this integration should be done in 2 parts. So one by one if you solve, let us not discuss here. So if you do this derivation by your own, so you will get your final answer is equal to 8a by n square pi square sin n pi by 2. If you expand it, then it will get ft, the 8a, now n is equal to 1, so 8a by pi square, then sin omega naught t, so this is pi by 2, that means it is 1. Then next term 8a by, now 3, it will be 9 pi square, sin 3 omega naught t, now sin 3 pi by 2, sin 3 pi by 2 is minus 1, so that is why it is minus. The next term will be 8a by 25 pi square, then again sin 5 omega naught t. So in this way Fourier series expansion can be written. Again we have a similar example. You see, this is a half rectified sine wave. Half rectified sine wave, you see this is a periodic function. This is a periodic function, but it does not possesses neither even symmetric nor odd symmetric. Okay, so this is actually original function ft. So you need to generate even part of it by doing this f of t plus f of minus t, and you need to generate odd part of it half by using this equation. So this is ft, so this will be minus ft. So second diagram. So when you add, similarly just like the previous example, it will simply be joined like this, and this magnitude will become 120 volt. It is simple. It's 120 volt because it is by 2. And if you extract the odd part, then it will be simply a sine wave. Okay. So with a magnitude of course 120 volt. So odd part you can easily write 120 into sine omega t. That is very easy because it is a simple sine wave. However, even part, since this even part FET, it has some, since it has no negative part, so it must have A0. So A0, if we calculate, it should be 240 by pi by using this formula. Okay, so it's simple. A0 is nothing but integration sine omega t dt with limit from 0 to t0 by 2. It's 1 by t0. If you evaluate in this manner, sorry, it should be 2 by t0. If you evaluate in this manner, now since this magnitude is 120, you must let me write it afresh. So A0 is nothing but 2 by t0 integration 0 to t0 by 2 120 sine omega naught t dt, or simply omega naught t dt. You should omit this n. So if you evaluate this, you will get this result is equal to 240 by pi. So this is the DC value. However, now what about in case of AN? Now you see, let us try to figure out. You see this waveform is symmetrical about y-axis, so it is a odd function, it is a even function, no issue, even function. So Bn should not be evaluated. So Bn should be 0. We have already evaluated A0. Now what about An? So An is existing, we can understand. Now again we assume any time, arbitrary time. So if we go half time period advance t0 by 2, so we repeat, we observe that same value is repeating. So it is actually it is possessing the half wave event symmetry. So we will see An will be existing only for n, 2, 4, 6, so on. So we must evaluate according formula, appropriate formula. So An should be 4 upon t0 integration 0 to t0 by 2 ft cos n omega naught t dt. So in this way, if you evaluate, so An should be equal to minus 480 over pi n squared minus 1. So ultimately, when you write the entire equation or entire expansion, so you see 240 by pi, this is the DC term, 120 sine omega t, this is the actually odd part of the function, which does not require any expansion because it is itself fundamental sine wave, and the remaining part is the even part, which is actually split in, or which is expanded in this form. So we have n, so we have cosine terms, right? So these are the derivations given. You can go through them. So with this, the topics on Fourier series is almost completed. Just to quick recap, we have started this chapter by stating that Fourier series is a mathematical tool to represent any periodic function into a DC term and then cosine and sine terms of nth order harmonics. That means summation of nth order harmonics. That means A1 plus A2 plus A3 with all a's we accompanied by cosine terms, and B1 sine omega naught t, B2 sine 2 omega naught t, and so on. And we have evaluated A0, An, Bn. From there, we have seen different type of symmetric waveform, symmetric periodic waveform. There we have seen if you possess, if any waveform, for an example, if it is a odd symmetric waveform, we should not calculate A0 and An, we must calculate Bn, because Bn will be only existing. In this way, we have studied different conditions. And then we have also understood that if a periodic function is there, it does not necessarily does not have any symmetric at all. So if any periodic function does not produce any symmetric nature, even symmetric and odd symmetric can be formed out of the parent mother waveform. So we have solved 2 problems on that, and we have seen many problems, and most importantly, if a partial waveform is given and the conditions are given, then we can form the entire waveform. So with this, I am ending this session, this Fourier series session here, and of course with this, this entire course, that is network theory, is ended here. I hope the entire session, starting from the very basic principles of network element, that is resistance, inductance, capacitance, we have crossed 10 long modules. I hope all these modules, all these materials will be helpful for you, for your academic preparation, for your GATE preparation, and if you follow them, I hope you will thoroughly enjoy the lectures. Thank you.